Hi, I'm Rishabh. I'm a PhD candidate at UC Berkeley, and today I will tell you about some new practical attacks that we've developed against encrypted databases that can be used to learn private content by observing only the volume of results in response to queries and no other leakage. And this is joint work with my wonderful colleagues at Berkeley and Princeton, Stephanie, Jianan, and Raluca. We consider applications that allow users to interact with an encrypted database at the server with the help of a client program. In particular, users can issue queries that search for keywords, and the server returns all documents that contain the keyword. In this setting, we are interested in understanding the capabilities of attackers who observe only the number of results returned in response to the search query, but learn no other information. The attacker wants to learn the content of the queried keyword and may obtain the volume information by monitoring the communication, or it can be a server-side adversary. Doesn't matter. The only assumption is that it is able to learn the number of results. Now, a line of recent work has shown that the volume of results can be a potent source of leakage. Our attacks differ from existing work in the following ways. First, prior work demonstrates how to recover the contents of the database using volume leakage from a series of range queries. We, on the other hand, target keyword recovery from search queries. But more importantly, these works make a set of assumptions on either the queries that are issued by the user or the data in the underlying database. For example, the user might need to issue close to all possible queries for the attacks to be successful, or the assumption might be that the underlying database is dense. These assumptions may not be realistic or feasible for many applications, and our aim in this work is to understand, is it possible to leverage volume leakage without making any assumptions on the queries or the data? We find that it is, and how are we able to achieve this? Our approach instead is to examine existing real-world applications and exploit the behavior of these applications, which allows us to avoid assumptions on the data or the queries. In particular, we find that many existing applications exhibit two key properties that help volume-based attacks. First, it is known that many applications support file injection by design. That is, they allow the attacker to insert files into the victim user's database. For example, email services or message forums. Anyone can send an email to the victim user, and the server will add the email file to the user's database. How can file injection be used for volume-based attacks? Well, if the attacker inserts enough specially crafted files, it can potentially induce a unique and known volume count for each possible keyword, and thereby identify a queried keyword in the future based on the volume of the results. But file injection alone is not practical because the attacker would need to craft and insert a very large number of files proportional to the size of the database. And this is where our second observation comes in. We find that many applications automatically replay queries without user intervention if they do not receive a response within a certain time period. That is, the client sends out the initial query and waits for a response. If it does not receive a response soon, it automatically replays the query. A reason for this behavior is to deal with network fluctuations and transient failures. And to understand how prevalent this behavior is, we studied 11 different web applications that allowed file injection by design. And we found that in nearly half of these applications, the web client automatically replayed queries if it received no response within a certain time period, which illustrates how common this behavior is. And this brings us to the contributions of our work. In this work, we show that volume attacks are practical without making assumptions on the data or the queries, by exploiting the behavior of real-world applications instead. And a point to note here more broadly about volume-based attacks is that they affect even sophisticated cryptographic schemes, such as ORAM or PIR, since these schemes typically reveal the volume of results, even if other sources of leakage, such as access patterns, are plugged. Next, we design a suite of attack algorithms, a basic attack followed by 4 advanced attacks, and demonstrate their feasibility by attacking the inbox search feature in the Gmail web client. In this talk, I will not have time to go into the details of all the attacks, so here I will only describe the basic attack with the help of an end-to-end example. The more advanced attacks build on top of the basic attack. So coming back to our setting, consider a user who wants to search for all documents that contain the keyword flu. The client program sends the query to the server. In this case, the word flu is present in 3 documents, so the server retrieves these documents. The first step for the attacker is to observe the volume of query results, which is 3 files, and the attacker then drops the query results. This is easy for a server-side adversary. Step 2, the attacker starts with a dictionary that contains a list of all the potential keywords of interest. So the attacker is interested in identifying the queried keyword only if it belongs to this list. The attacker then divides their dictionary into k partitions, for examples k equals 2. Step 3, the attacker uses the partition dictionary to carefully craft k files, such that all the words in partition number I are inserted exactly into I files. So in this case, the words asthma and cancer, which were in partition number 1, are inserted into one file each, while the remaining words that belong to partition 2, including the word flu, are inserted into both the files. Step 4, the attacker injects these files into the database at the server, and the server updates the database with these files. For example, if this is an email application, then each file is simply an email sent to the victim user. Step 5, the attacker waits for the client program to replay the query, which it does after a time because it hasn't received a response. The attacker then repeats these 5 steps in a sequence of rounds. In response to the replayed query, the server this time round sends 5 files, which is 2 more than before. The attacker observes that there are 2 extra files in response to the same query, and therefore the queried keyword must have belonged to partition number 2, which allows the attacker to narrow down the potential list of keywords further. Once again, the attacker partitions the remaining dictionary into k equals 2 parts, and carefully crafts 2 files. The word flu is inserted into one file, while the words in the second partition are inserted into both the files. The attacker then injects the files into the database as before, and waits for the client to replay the query. This time, the attacker sees that there are 6 files returned in response, which is 1 more than before, and so the queried keyword must have belonged to only one newly injected file, and hence it must be the word flu. This completes the attack. A quick analysis of this basic attack's performance. The attack essentially only requires log d query replays, where d is the size of the attacker's initial dictionary. This is because in each round, we narrow down the dictionary size by a constant factor of k. On top of the basic attacks, we design a suite of advanced attacks for more complicated scenarios, such as when the client does not replay queries, or it pads the volume of results, or when the volume measurements are noisy, or when queries contain multiple keywords. Please read the paper if you're interested. And to demonstrate how practical volume attacks can be, we perform our attack on the Gmail web client. The setup for the attack is as follows. The user uses the inbox search feature in Gmail's web client to retrieve all emails that contain the queried keyword. Since we do not have access to Gmail servers, we simulate a server-side adversary with the help of a man-in-the-middle proxy and use it to learn the volume of returned results. Before performing the attack, we studied the application to understand what attack parameters were viable, and we found that the client replayed queries every minute or so, and within that time, the server could safely update the database with 36 emails, implying that the attacker should inject no more than 36 files every round. We use these observations to attack the Gmail web client against a variety of dictionary sizes, from 10 to 100,000. And for reference, the English language dictionary contains about 300,000 words. We found that the attacker only needed to inject tens of emails for a successful attack, and that the attack completed within a matter of minutes end to end, which demonstrates their practicality. So, in conclusion, in this work, we present new attacks for recovering queried keywords using only the volume of results. Our attacks exploit the behavior of real-world applications instead of making assumptions on the data or the queries. We demonstrate the feasibility of our attacks on the Gmail web client. And in the paper, we also describe more advanced attacks that build on top of the basic attacks, along with detailed theoretical and experimental analysis. We also discuss a set of mitigation strategies against our attacks. So with this, I will conclude my talk, and thank you for your attention.